So, good morning, everyone. This is Mohamed from Northumbria, UK, and I'm here today on behalf of my colleagues Pablo Martinez and Omar Doukari, and this talk about scenario-based material flow and circularity assessment of deep renovation projects. And we use the BIM circularity framework to assess the material flow and circularity during renovation projects. And before I get into BIM and the digital details, I wanted to talk about the core issue of construction waste. Nowadays, the construction waste management practices are broken. Construction projects are often planned and optimized for time and cost, never for waste. And waste is treated as a byproduct. We quantified it after the fact and never integrated into planning decision. Also, waste is often quantified at project level, not at activity level. So we always know how much waste is generated, but we don't know why and when the waste is generated. And the renovation makes this worse. We should consider special constraint, resident disruption, and the coordination constraints. And on the other hand, regarding circularity, always operates at building a system and never link it to individual activities or schedules. And no scenario sensitive models exist to evaluate how renovation depths affect circularity rates. And no BIM integrated models has been utilized to quantify circularity during planning stage. And what we do to address these gaps, we develop an integrated framework that linking BIM with scheduling constraints, including spatial constraints and disruption constraints, with along with material flow modeling. And we trying to enhance the construction waste management during the planning stage, each stage using two indicators, circularity index and waste recovery potential. And we assess how renovation depths affect circularity rates. And to achieve these objectives, we develop a tool called the Circular Intelligent Waste Engine, which we can integrate with any BIM models. The Circular Intelligent Waste Engine framework has 5 stages. The first stage is physical asset, including BIM model, renovation scope, and geometry, material quantities. And the second stage related to defining the activities through performing work breakdown structure and considering production rates of renovation activities and calculating renovation activities duration using the total quantities divided by the production rates. And the third stage about waste computations. We quantify waste through using the quantities extracted from BIM model, and we added to it the expansion waste coefficient to calculate the real volume of waste at activity level. And then using the extracted data to quantify the circularity index and waste recovery potential. And finally, developing a pre-designed decision support tool through performing different renovation scenarios and to find the optimum scenario. We tested our framework using a real French case study. A real residential building which has 30 apartments and 5 floors and about 1,120 square meters. And the building was occupied during renovation. And we have developed a BIM model with a level of today 350 to apply our framework. 3 scenarios. We run 3 scenarios with different criteria. The first scenario scope is to perform some renovation to envelopes and heat pumps with ventilation. The second scenario, we implemented the same renovation activities like scenario 1, and it changes the system of ventilation with mechanical ventilation with heat recovery with solar energy. And the third scenario builds on the second scenario with a thermal solar. And also there is a difference between the construction process for each scenario regarding how many activities working in parallel. The first step for our framework is we build our work breakdown structure by defining each activity per zone in each floor. And this produces the activity zone matrix to show the special distribution of renovation workers. And also we use the precedence network to define the vertical and horizontal sequences constraint. We also define the type of equipment we will use during renovation projects, because each tool has a unique daily waste generation. And the main objective of the circular intelligent waste engine to bridge the BIM model with renovation scheduling through considering special constraint in specific. And the main output of the tool is to quantify and calculate the daily waste time series per activity. And we use this daily waste time series later as inputs to calculate circularity index and waste recovery potential. And we use some coefficients derived from previous studies and with informed expertise calibration to calculate both circularity index and waste recovery potential. And look at this results. You can find here that for the third scenarios here uses most of materials, but however it generates the least quantities of waste, and that's because installation-based works generates less waste than demolition-based works. And that means that higher material inflow don't ever translate into higher waste. And that deep renovation shift activities makes towards lower waste in installation-based works. And this sneaky figure shows to us where waste goes. You can see here that out of the total quantities, which 49,000 cubic decimeter, about 25 of this waste can be reused, and about 46 of this waste can be recycled. And this gives us about 71 that can be recovered. And if you look at this daily waste generation profiles across the three renovation scenarios, you can see here that the first scenario, which is a solid line, peaks at about 377 cubic decimeter per day. That is about 2.8 times higher than scenario 3, which is more smoother and more flatter. And that give us important point about that scheduling structure controls and governs the waste intensity, not the renovation depth or the duration. And finally, regarding the circularity index, we can see here that the circularity index has been increased from 0.58 in scenario 1 to 0.65 in scenario 3, with a total improvement about 12%. And regarding waste recovery, we can also notice that the waste recovery potential has been increased from 0.67 in scenario 1 to 0.74 in scenario 3, with a total improvement about 10%. And we found that the third scenario achieves the highest circularity index and waste recovery potential. And that means that deep renovation scenarios achieve higher circularity index and waste recovery, demonstrating the decoupling of materials throughout the waste and waste generation. And the conclusion here is about the main conclusion is that we have developed an integrated framework that links BIM with with an automated tool to enhance construction project scheduling through considering special constraint during the planning stage. And also how we can use some circularity indicators to enhance construction waste management practices during the design stage and during the planning stage. And we have developed a pre-designed decision support tools that help us to enhance the construction waste management practices in general, and to enhance also the operational resilience of construction process during planning and design stage. And regarding its limitation is that it is a single demonstration case. We need to test it in multi-buildings. And in the future work, we plan to quantify the recent disruption and trying to perform some multi-objective optimization to find the near optimum scenarios for renovation, and to develop some operational resilience indicators to enhance the construction waste management during the design and the planning stage. And that's it for me today. Thank you very much for listening. I'm ready for your question.